Please let me have your attention. It's a great pleasure and an honor to introduce the first Myron Lecar Prize lecture. Mike Lecar, we all knew him as Mike, was an astrophysicist at SAO for more than 40 years. Let me first acknowledge Helene Lecar and her two sons, Matt and Josh, and daughter-in-law Jill, who made the long trip to be here today. I'm saddened that Harold, Mike's brother, who passed away earlier this year, couldn't be here. He would have been very, very proud of this event. Mike joined SAO at the invitation of Fred Whipple after completing his graduate work at Yale and after being one of the founding members of the NASA Goddard Institute for Space Studies in Columbia. Mike's work ranged from Vanguard 1 satellite, with which he made one of the first measurements of the J2 of the Earth, one of the first scientific measurements with a satellite. It spanned through cosmology onto the study of planet formation, extrasolar planets, and solar system chaos. Mike was particularly proud of his role in establishing the WISE Observatory, which you see there, the first astronomical observatory in Israel. He spent a significant amount of time in Israel during the planning, construction, commissioning phases of the observatory, and it's still in operation today. Mike was also one of the founding members of Harvard's Origins of Life initiative that's led by Dimitar Sasolov. Mike was a generative character with many friends and many colleagues. He taught countless freshman seminars. Some of his students eventually went on to become chairs of their respective astronomy departments. It's kind of amazing. There's a record of somebody who was a freshman, and you see where they are today. He could have a very big impact on people. He nurtured careers, he mediated disputes, and spawned collaborations. And over the years, he became kind of an elder statesman for the observatory. So it's fitting that Mike would provide in his will for the endowment of an annual lecture on the topic of theoretical astrophysics or extrasolar planets. So when Sean Andrews, Dimitar Sasolov, and I, the selection committee, met, we all independently nominated Doug Lynn as our first choice. Many of you will understand why he's the obvious first choice. He's an outstanding theoretical astrophysicist with an extremely broad range. He is an expert on planet formation. His early work on planet migration presaged the detection of hot Jupiters, and his 1996 paper on orbital migration of 51 Peg-B, the first detected extrasolar planet around a sun-like star, is still highly relevant today. And nothing I can say can really do justice to Doug's abilities as a scientist, but kind of beyond that, Doug was a very close friend of Mike's, and so I believe from their time at the other Cambridge and Doug's time here as a postdoc. So like Mike, Doug has a joke for every occasion, mostly clean. He's quick with a pun, mostly painful. So consider yourselves warned. So with that, let me turn the floor over to Doug Lynn.
Thank you. It is my great pleasure to be able to be here today to join this celebration of the accomplishment of Mike Lecar. And what is close to his heart is always been solar system dynamics. And today there has been an explosion of information. Partially comes from radio velocity measurements, and some of which actually started here with Dave Latham's discovery. And today we have over 1,000 exoplanets, and we can start to do some statistical analysis, and which was not possible only 20 some years ago. So we have now evolved this origin of planets and planetary systems from sheer hypothesis of past event that happened long ago to a branch of science where we can test our ideas and assess what is really the most important and relevant process that's regulating the emergence of planets. And of course, I should say that the other great advancement in addition to radio velocity survey has been the discovery that's made in the past few years much of that activity has been centered around here, and that is really this discovery made by Kepler Space Telescope, and which led to the discovery of well over 2,000 planetary candidates. As you can see, that we are starting to get some patterns in their basic characteristics, such as their period size or period mass distribution. So I would not go into much of the observational data and only draw out the relevant parts that supports a coherent story I would like to share with you. Like a true theorist, you only pick those observations which are fulfills the appropriate strong points you want to advocate. So now, and even in theory, I will be selective, and I shall waste no time in getting to the theory which I feel much closer or more at home with. That is the so-called sequential accretion scenario. And there are other scenarios, such as gravitational instability, and which perhaps account for some of the planets. As you can already see from the observation today, that the most common planets are not the gas giants, but the super-Earths, and perhaps there is yet another huge population of entities to be discovered, and they are not so super-Earths. And for those, and perhaps the more common and scenario, or that which makes sense, will be something that is a gradual build-up process. Process starts from a protostellar disk, which was hypothesized by a theorist 200 years before it was discovered. And in this disk, gradually heavy elements condense into grains, and grains grow into planetesimals. The detection of the first protostellar disk was actually also made here by Charlie Lada and his collaborators. And today we now know the property of much of these disks. And I will use a few minutes later to discuss how they are relevant to the formation process. And some of the key process, I mean, this idea of sequential accretion process is not new. But along the way, there have been giants, intellectual giants, who have thought about all of the challenging issues associated with this scenario. And for example, starting with the grains, how do you retain them? How do you condense, build up, and retain them? And this was first posed as a major problem by Fred Whipple, and then later on, when these objects grow into sizes larger than kilometers, when they collide and they tend to fragment, and this was also a problem that has been analyzed, suggested by Willie Benz, and then later on by Sarah Stewart. And then there's also these issues when you start to grow these planetesimals, and eventually they run out of building block material in their immediate neighborhood, you get into what is called isolation mass. So let me address these three challenges in a very short time. So the idea of these barriers is that these building block material form not in isolation, but in the presence of gas. And the gas actually interact with these objects, and the gas may not necessarily move at the same speed because there's a pressure gradient across the disk, and the gas tends to move a little bit slower than these grains. So there is a headwind, and they tend to move towards the center. So this has been a important issue. How do you retain them and build up to larger objects? Many suggestions have been made, including various type of instabilities, and they all have some problems of their own. So what I'm going to suggest today is sort of reviewing all of these different processes by saying that there is a last way to mechanism that you can still retain all of these material, and it's not magnetic fields, and only partially. So what you do is that these grains may indeed migrate towards their host star, but eventually they will stop somewhere, and usually they stop at the inner edge of the inner cavity. These disks are not completely attached to their host star, and they get very close to their star, and usually, and we realize today that many of them have these cavities in the center and possibly carved out by the stellar magnetic field. And this region, they will stall and they will slow down, and whereas the gas would be accreted along the field line, and they will stay near there. And while there, they don't really go anywhere because that is a local pressure maximum. Inside the cavity, there is no gas, there's no pressure, and outside, and there's a peak and then declines. So this is the region where the gas flows at Kepler speed, and material can accumulate near there. So they can build up, and when they get to kilometer-size barrier, and they may fragment, but they don't go anywhere. They will stay there and stay there and stay there. And it's a little bit like a river coming down from the mountain, and they go to a region where they slow down, all the sands gets left behind, and if you have a bridge near there, when the sand builds up to be large enough, the bridge will collapse. So eventually they will form these gravitationally unstable part of the disk, and they can grow into larger objects. And once they grow into these larger objects, they will start to build up to larger and larger pieces, and locally, stay there locally. Of course, most of the volatile gas will probably be evaporated, and what you left behind are the refractory cores, and from where things can build up. This is a subject that was close to the heart of Mike Lecar, and in fact, in a paper he did in 1986, along with Arsev, and they use a state-of-the-art embodied simulation to actually try to look at the growth of these objects in the absence of gas. But I'm looking here at the possibility of growing the very first embryo. Now, as they grow, eventually these planetesimals will start to collect other planetesimals within their feeding zone, and they can perturb each other's orbit and to generate velocity dispersion, and they will start to merge and coalesce and merge. But eventually they will use up most of the material within a few times their Roche radius in this feeding zone, and they start to become dynamically isolated, and this is what some people refer to as the start of the oligarchic growth stage. And they will start to have a upper limit in their growth. I never know which way yes, this is probably the way I should push. There, right. Here, so this is the width of their Roche, this is the Roche radius or the Hills radius. This is the width of their feeding zone, and when they empty out their feeding zone, they get into an isolation mass. So George Wetherill realized that if you use a minimum mass nebula model, and this isolation mass is only a few times that of the moon, and you can never form a large planets this way. However, this isolation mass is dependent on the surface density to the 3/2 power, and if you have a continuous supply of material that keep on coming in to these region of the riverbank, and the sigma will increase until this isolation mass will grow. Now, what happens next? Surely we have lots of planets formed at very large radius, not all close to their host star. And let's see what we can do. So the next stage happens is that these planetesimals will start to interact with the gas nearby. And the first thing they will do is that they will perturb the flow of the disk on the inside as the gas moves around, and they experience a little gravitational pull towards these protoplanetary embryos, and they will excite a spiral density wave. And these density waves are very similar to those observed in disk galaxies. In fact, we even use the same terms as these type of streamlines which pass the orbit of the embryo in the rotating frame. They continue to move around like this, and they will tend to experience what is called a Lindblad torque, and it's associated with Lindblad resonance. Now, whereas the inner part of the disk transfers angular momentum through the Lindblad torque to the embryo, and the embryo then transfer angular momentum to the outer part of the Lindblad, outer part of the disk. And any imbalance will lead to an orbital migration for the embryo. But in addition to that, there's also these streamlines that undergoes a horseshoe orbit type of pattern. And these are called the co-rotation region. And in here, there's also apparently a torque. Now that torque gets wiped out eventually. The reason for it is that when the gas streamline passes through this part of the azimuth and going from the inner part of this horseshoe orbit to the outer part of the horseshoe orbit, it needs to gain angular momentum, and it gains from the embryo. But these streamlines is going to come back to this part again, and it's going to lose angular momentum to go inside. And if there is these two parts are exactly balanced, then you don't get a net gain or loss. However, if there is a flow of gas from the outer part of the disk to the inner part of this through the action of viscous stress, and then you can maintain a surface density gradient, and such that you can actually exaggerate this co-rotation torque. This process has been studied thoroughly, first on a whiteboard in the notes of Mike Lecar, and where he talks about the torque, and that is associated with different regions of the disk and with the embryo. Now, but this has also been thoroughly analyzed with numerical simulations, and many of these simulations has described and these torque in terms of a basic linear analysis and the quantity that you can get from just order of magnitude dimensional analysis. And you can find that this torque is dependent on surface density, and it's dependent on the mass ratio and the scale height. But in front of it, there is a coefficient. And these coefficient is determined by the structure of the disk and the competition between viscous transport of angular momentum and the tidal transfer of angular momentum, and whether they can match, whether they can satisfy the condition for exaggeration. Now, I really hate that word, exaggerated or exaggerated. You would have thought exaggerated means you get the full amount. In fact, it's the opposite. When it's exaggerated, you get nothing. When it's exaggerated, you get the full amount. And so there's a range of mass in which you can actually get the full amount of co-rotation torque. In certain regions of the disk, and that co-rotation torque is able to push the planets outwards and to give you an outward transport, and furthermore, it can be stronger than that you can find from the differential Lindblad torque. And these are the region in the inner part of the disk where the disk is primarily heated by viscous dissipation. But in the outer part of the disk, the disk is heated by surface irradiation. And in that part of the disk, and the differential Lindblad torque always tends to win to give you a inward drift. Here is plotted in these figures, and this is the radius, and here is the mass of the planet, and the blue lines means the blue region means things are moving in, and the red region things are moving out. This is not the political map of the last election, but nevertheless, there are these regions where you can see the blue meets the red, and these are regions, the inside is moving out, the outside is moving in, so you get a trapping location. So now you notice that there are regions in here that things are moving out, so if you build up large enough to be relatively large embryos, and they can start to move out, and they will move out relatively quickly. And here are some calculations done by various undergraduate students I have the privilege to work with in China. And so what they show is that when these embryos become relatively large, and they can start to move outwards. And along the way, if there are any planetesimals, if the planetesimals are relatively large in size or very small in size, and they can be dragged along as their eccentricity gets excited, they can, because they get trapped onto resonances, and if their mass is either large or small, and these eccentricity can be damped by either hydrodynamic drag or tidal drag, and as a result, they can get carried along. But if their mass is somewhere in the intermediate range, and for example, 500 kilometers, or even up to lunar size, and as they gets pushed along, their eccentricity gets so excited, eventually they cross the orbit of the embryos at their periastron, and they can get scattered through close encounters. Regardless, this process tends to move things into these trapping zones. Here is the time, and this is the location, and as you can see from the inside is moving out, outside is moving in. And there's this general tendency for things to get together. But when they get together, they start to influence their mutual streamlines, and they can cause corrotation to these regions for the streamlines to actually cross over with each other and have enhanced mixing. So the next step is why do I want to talk about this? Well, the reason for it is that these embryos would tend to move, and they don't necessarily get together. And when they move, as they approach each other, eventually they try to keep each other at arm lengths, provided they come in relatively gently. This is like piling up a whole bunch of eggs. If you gently put them there, and they can be well separated. But if you try to push the eggs together too fast, they will break the eggshell and they will merge, and you'll get them scrambled. So now, why do I want to say this in the context of planet formation? Well, around solar-type stars, we have about 15 to 20% of the stars have masses comparable to that of Jupiter. But more than half of them have a super-Earth with mass that is a few times that of Earth. And there may be many more planets around many of these systems that's below the detection limit. So if we start to add up the mass of all the super-Earths in system that without gas giant, and we'll see that their total mass add up to well above 10 solar masses. There's no shortage of building block material in many of these systems. And the amount of mass in these systems are more than all of the terrestrial planets in the solar system put together. And they don't have, around each star, and they don't have gas giants. So the fact that you have a formation of gas giant is not the consequence of lack of material. It's the consequences that they couldn't get their act together. So, how do they get their act together? So what is the way to get their act together? Well, as I said before, if you can push them fast enough with these eggs, and you can have a merger. So how do I make them go faster? Well, the migration rate is a function of the local surface density. Now, if the surface density is high, I can then push them fast, and then I can get them in together. Okay? Now, but observationally, how do I measure the surface density of a protostellar disk? It's very difficult. I can do that with accretion rate, and I'm going to come back to that in a minute. Okay, now furthermore, in these systems, you have these regions of convergent migration of trap radius. So if they come together, and as they try to get, if they get sufficiently fast, and they will start to cross each other's orbit, when they cross each other's orbit, and they will undergo close encounters first. And if they go through close encounter in the absence of gas, what happens is that they will spread out and they will scatter, and this is a well-known problem that many people have done embodied simulations, starting with a packed system, and they run in time and they undergo close encounters, even if they a few gets merged, but there's a spread. But in this environment, in the background of this gaseous disk, and even after the scattering, they will come back. They will return to this trapping location, because on the outside, if they get scattered to the outside, they will migrate in, scatter inside, they will migrate out. This is like the snowboarders on these hot pikes. And they roll up and down through these hot pikes, and they may undergo lots of close encounters, but sure enough, they will undergo some collisions. And when they do that, eventually their mass will increase. Now, there is a question to say that when the mass goes up to a certain value, can we start to produce gas giants? And that is in this region. These are the observed systems. And we can see that many of these systems are found in these large radii of order a few AU. Now, so what happens when they collide? If they collide with relatively modest speed, and they can merge, but if they collide with relatively large speed, and they could actually even destroy each other a little bit. But this type of process can build up the core, and if they repeatedly get trapped into these locations. When the mass of these embryos are small, and they only attract the planetesimals because the gas in the background has too low, their velocity, their sun speed is relatively high, and they cannot experience the gravitational pull here and to be able to stay around this region. Okay, but when the core becomes sufficiently massive, they will start to accrete gas. But unlike gas accretion onto black holes, and what happens is that these gas must rest around the core. So that means that they have to liberate a lot of energy here. But it takes time for this energy to go out. So that time is the Kelvin-Helmholtz time scale. It was realized by L. Cameron almost 30 or 40 years ago that this time scale could be very long. L argued that in these regions, that these envelopes are fully convective, so there's energy transport, but in the outer region, there's still got to be a radiative layer. In that radiative layer, the transport is inefficient, so as a result, eventually this growth by accretion, gas accretion, is slowed down. However, if you make the core sufficiently massive, then you can start to accrete like crazy. Okay, that critical mass is somewhat not exactly determined, but is about 10 Earth's mass or so. You need to do all of this within the time scale of the gas depletion time. And again, here I'm trying to marry the two communities, the star formation community and the exoplanet community. I know this is a difficult thing to do here, and but you can actually see that this process, these competing process, is what determines the outcome. Now, so let me briefly summarize what I just said, that whether you can form gas giant or not is not due to the lack of material, the lack of time. It is due to whether they can get their act together. And this is precisely the reason why when we look at these mass distribution or size distribution, we see that many systems around solar type stars have large number of super Earths, a much smaller fraction of gas giant. So what about the dependence on the stellar mass? Now, you can run this type of simulation over different mass accretion rate, which determines the surface density and these three different columns, or different masses. Okay, and you can check these mass, 0.5 solar mass, 1 solar mass, and 2 solar mass, and you see they're relatively similar. So that means that what they depend more on is the accretion rate than the mass of the whole star. Okay, you say, wait a minute. We know that there are many more gas giants around high mass stars than low mass stars. And you're telling us they are all the same. Well, let's just wait for a moment. And if we go back to the determination of mass transfer rate around T-Tauri stars, the classic work of Lee Harmon, which was done here. And if you look at the stellar mass and versus the accretion rate, which is determined by the UV veiling and some of the emission lines, and you will find that for a given mass, there's a large spread. There's a large spread and factor of a few in this accretion rate. Secondly, the mean accretion rate is an increasing function of stellar mass. So then you can work out for the critical mass accretion rate for different stellar mass, what is the fraction of stars that has accretion rate larger than this value, so then the embryos can get together to form a critical mass core. You find 0.5 solar mass objects have much less than the 1 solar mass than the 2 solar mass. And perhaps this is the reason why you're seeing this mass dependence on the fraction of stars with planets, and another piece of work that was done by John Johnson. So we see that this is not limited to just the stellar mass. As you know, there's also a dependence on the stellar metallicity. Now, in fact, if we look at the gas giants, and you see that at high metallicity, there is a real turn up, and in terms of the number of stars with gas giants. And we can also do this for stars of different masses, and looking at, for planets of different sizes and masses. And we see that here is metallicity, here is a radius, and based on much of the work that's done here, and we can see already that the gas giants tend to be the ones which are preferentially found around metal-rich stars, but the super Earths, even though there may be much of the material, and they're found around stars with almost any metallicity, down to 0.06, minus 0.6. So what that's telling us is that there's, again, no lack of material. Even around low mass stars, I can form plenty of super Earths. It's just that they didn't get their act together. Okay? And so that process made us to think whether there's some metallicity dependence. And if you change the metallicity, you change the temperature in the midplane for a given accretion rate, and therefore you change the region where things could be dominated by outward migration. And this process enables us to look at the critical mass, the critical m dot that is needed for embryos to come together and to get into overlapping orbit crossing region, and that for the metal-rich system is much lower than the metal-poor system. We can also fold in the effect of snow line, because across the snow line, the opacity change by the sublimation of the ice grains, and this can also change the merger rate. So all of these things suggest that, in fact, there is a tendency for both mass dependence and metallicity dependence that is not just based on the availability of materials. Once you form the first gas giant, and the gas giant will start to strongly perturb the structure of the disk and generate spiral density waves, open up a gap, and start to migrate on their own through type 2 migration. And some of these type of structure may have already been seen from ELMA type of results. So the next step is this question about retention of gas giants and the question of multiple gas giants. How do we form them? How do we form so many of them? First of all, I have already, using this migration process, I was able to concentrate all of the building block material into one very narrow region. So in fact, the time scale for formation now becomes much shorter. But what about the possibility of forming the next guy and the next guy? We want to form them before the gas has gone away. And there is some indication that if you find around any given star, you find one gas giant, the possibility of finding the second is greatly enhanced. More than 50% of the system has one gas giant, shows signs of its additional gas giant. So perhaps this is a process that you can see maybe there's an enhanced formation process. Let's think about how that could work. Now, this process occurs is during the growth of the gas giant, it changes the local gravitational potential. And it starts to pick up the gas, and it starts at the end point of this runaway gas accretion. The growth rate is so large such that it will perturb the orbit, and it will cause about a fraction of them will actually get ejected inwards, a fraction will ejected outwards, another fraction will collide directly with these emerging gas giant. Okay, let me just show this slide one more time. Let me see if I can do that. So if they in fact merge like this, and they will completely change the core structure they had to start with. And perhaps this is the reason that we see a diversity in the internal structure between Jupiter and Saturn. So let me move on to the next slide. Okay, here it is. So the formation of a gap causes some material to get ejected in and out. But the migration, type 1 migration, will bring them back. Except this time, they can't get into the gap because by the time they get close to the edge of the gap, they feel the pressure, they feel the surface density gradient, and the combined effect of co-rotation and Lindblad torque will cause them to get stalled there. When they get stalled there, they accumulate, and you can form additional companions. And this is probably a way to give you the formation, enhanced formation of multiple systems, and with relatively close spacing. And during that initial stages, when they still have gas around, even though they're relatively close, they can perturb each other, but the presence of the gas will damp their eccentricity out, so they can have orbital crossing time that is relatively long. But the moment the gas goes away, and they can start to undergo relaxation and dynamical instability and relaxation, and they can give you this dynamical diversity. Here is a measure of orbital eccentricity versus semi-major axis, and as you can see, many of these systems are very much unlike the solar system, and they have large eccentricities. And in fact, this is also an area that Mike Lecar has done some classic work with Franklin and Matt here. And here is the modern day update by Rosemary Martlin, where she looks at when you have packed dynamical system and whether they have overlapping resonance and whether that can lead to relaxation. The dynamical stability tells you that when you have multiple systems and there's a tendency for these systems to get excited and to generate large eccentricity. Okay, so what happened to the gas giants? The gas giants themselves, and in the presence of this evolving disk, would also start to move, and their orbital evolution is somewhat locked to the viscous evolution of the disk. And again, here is a pioneering one of these freshman seminars that Matt has referred to, where Mike draw these type of figures and try to explain to freshmen and undergraduates. And so the basic idea is that these tidal interaction is coupled with the viscous evolution of disk, causing material to migrate. Along the way, if there's something else along the way, and they can actually capture them into mean motion resonance, and we see plenty of these type of evidence. And here are some of the simulations that one can see in an evolving disk as the disk evolves, and the region which separates the viscously heated and the irradiated region move inwards because the viscous dissipation is diminishing, and as a result, you can have them, the system form a large distance and then migrate in again. During this migration, if you have super Earths along the way, and the super Earths can be carried in by some of these gas giants, and in systems such as KOI 94, where you see a gas giant outside a core, and this is the smoking gun for core accretion and migration. Now, what happens when they keep on going? They keep on depleting. This green line represents the boundary of the trapping radius. The planets, if they're massive enough, they will start to migrate inwards. However, at the same time that these stars have a strong field, they can maintain these kilogauss field for more than 10 to the 7 years. And during the depletion of this, the field essentially remains, but with the disk depletes, and then this magnetospheric cavity will start to expand. Now, the super Earth tends to get stuck onto the walls of magnetospheric cavity near here, and the reason for that is that they rely on the balance between co-rotation torque and Lindblad torque. Whereas the gas giants, they tend to undergo type 2 migration. They get into the cavity, and they don't care how big the wall of the cavity is. So during the expansion of the magnetospheric cavity, the gas giants remain inside this region, whereas the super Earths can get carried away to move out a bit, reverse their migration direction. And perhaps this is why we see that there are 3-day cliffs, and but maybe with a super Earth, and this would be slightly different, and as things migrate in, and eventually as the magnetosphere expands, and then you can have a reversal of migration. And if this is a possible mechanism to account for the difference in the period distribution between the super-Earths and the gas giants. So, what is the evidence, observational evidence, to suggest this type of process may have taken place? Well, here is something that Kelvin Schlossman has done, and what he did was to look at all of the spacing of the multiple systems and normalize it against their mutual Hughes radius. So these are Hughes separation. And whereas the ones with very low Hughes separation, they're probably due to dynamical instability that would destroy them. But there is a drop-off at the high end, and that's a sign when you have a process that brings all of these things together into a compact configuration. Now, we see that in many of the systems, in these super-Earth systems, are near but not on mean motion resonances. So, so you say, well, your theory may have failed because they're close to resonance, but they are not on it. So, is there a way to get around to this? Well, if you have a multiple system that gets migrated out to this trapping radius, as they migrate in during the depletion of the disk, and they get onto the expanding magnetosphere, and eventually, as the disk becomes more and more depleted and the torque becomes weaker and weaker, they will exit. They will leave that expanding inner boundary, and as a result, depends on how fast the system, how strong the magnetic field is, how fast the system gets depleted. You can actually end up with either two of them come out together, or one come out and the other one is sort of gets exit at a slightly different stage. Okay, you can have different separations in the end. They don't need to stay on to these type of mean motion resonance. What about these highly eccentric systems? Well, they may undergo relaxation, they may undergo Kozai effects, some of them may undergo close encounters with their host star. And that's an alternative method of producing hot Jupiters through dynamical process. But one must be careful because in the process of these close encounters, if you don't come close enough and the system does not circularize, if you come too close, then what happens is that there will be mass loss and will cause these systems to escape. In fact, James Gulachan, who's here, has also done this pioneer work, and more recently, Shangfei Liu has done some of these things with a core. Let me move on. So if you have multiple gas giants, I think Josh Wynn was telling me earlier today, and talking about whether systems with these super Earths, whether they are lonely or they have multiple systems with some sort of a perturber, this still remains to be an outstanding issue. How do we settle whether it's this migration or scattering? And people have proposed maybe one way to do it is using the Rossler-McLaughlin effect, try to measure the obliquity, and much of that has been discussed here. And the important issue here is that the obliquity seems to be fairly random around stars which are relatively massive, and they are more or less aligned around stars which are low mass, and perhaps this is something to do with their host star and to do with the tides. One can analyze this kind of tidal argument. If all of the tidal components are the same, when you change the obliquity angle, you also change the semi-major axis in a big way, and they cannot survive. On the other hand, if you only change the obliquity angle, you would expect there to be alignment and anti-alignment, and there should be a concentration of them, and you don't see that. So is there an alternative way? I'm going to suggest, I'm always a maverick, and like all politicians, and whenever they're in trouble, they always call themselves a maverick. And I'm also no exception. And so I would suggest an alternative method based on the work of Tammy Rogers. And this is also something that is a phenomena people have observed on Earth, and is a process called quasi-biennial oscillations, during which some of these stream changes direction. The jet stream changes direction on every 28 months, not 24 months, and they can change these direction, cause major weather conditions. Well, this kind of effect is a little bit like a cat experiment. So you can do this experiment by going out there on the 4th floor and drop a cat with the leg up, and you drop the cat, and if there's no catastrophe, the cat will land on its feet. So now it starts out without angular momentum, it ends without angular momentum, and there's no torque in between. So how did the cat turn around? Okay, if you have a camera that shines on the head of the cat indeed spins. But there's no net angular momentum, so there's got to be differential motion. What is happening here? So in what we're suggesting is that these stars, these massive stars, are actually undergoing spin flips. Okay? And the reason for it is because they have convective cores and radiative envelope. And and add the interface, and they can excite gravity waves, and these gravity waves can carry angular momentum, a little bit like when you have convection, you boil an egg, paint one side of the egg red, and the other side leave it white. You put it inside a pot, you boil it, and you see the red turns around. Okay, it's keep on turning around because all of these plumes are pushing it. But these waves will propagate, okay, and it propagates through lower and lower density into regions where it's like a tsunami. And then eventually the amplitude will become nonlinear, and the wave will break, and it will deposit angular momentum. And that can change the angular momentum from the inside to the outside. You can get differential rotation, perhaps in 3D, even differential obliquity, and that experiment is being conducted right now by Tammy Rogers. Okay, so how do you test this idea? You test this idea using stellar oscillation and try to see from the split and the break of degeneracy, you can measure the rotation from the inside versus outside, and perhaps this is a mechanism. You can change the phase of the star rather than orbit of the planet. So there are still many competing physical processes, but my time is running out. And so all I'm going to do is to leave behind all of these issues, and just to impress you that I have actually thought about them. And this is a fantastic field. It's so rich, and you can enter it at any level, and I welcome all potential collaborators. And it's incredibly good field to be in. You can put all of these physics together and do a population synthesis and start to make predictions, and predictions, some of them will be false, and most of them will be false. But that's the process of science. It's a process of elimination. It's a process of eventually we will try to come up with theory with predictable mass period relationships, and what you don't discover actually tells us a lot of information. And it tells us certain type of process is not so important. Other type of process is important. And eventually we'll try to make these match and determine what is there. So here's my summary. And actually, forget about this summary. The basic take home is message is that whether you form gas giant or super Earth is not due to the lack of time, the lack of building material, but it's due to whether you can get your acts together. And I have been told about this when I was a youngster, and by my dear friend, I always refer to him as my Uncle Mike, and because he has this rabbi style. And and even when we had a big argument, and he settled it with a good meal in London, and I told him that I would like to have some classical salt beef, and completely kosher. He says, well, you know, I want to have Chinese food. So we found the perfect solution in London. It's called Cohen and Wong. On that note, thank you very much.
There must be some questions for Doug.
So, there's a risk I didn't hear you correctly, but did you suggest that either Jupiter or Saturn had undergone a major collision at some point in their history?
Well, first of all, if you have a core accretion scenario, okay, now you drain out the heavy elements and you put them into planetesimals, embryos, and cores. What does that mean? That means the gas in the disk is going to become more metal poor. So if you pile this up on top of Jupiter, inside Jupiter, and Saturn, the envelope should be metal poor. Okay? Well, it isn't. It isn't metal poor. It's in fact very metal rich, and 4 times to 10 times solar value. So how do you do this? Well, you can try to erode the core, and that's difficult because the core has heavy elements, so the molecular weight is difficult to tune out. You have convection try to do it, but it can't turn the rock up. Okay, so the great way to do it is you have not so late, but relatively late heavy bombardment. During the formation stage, it's almost certain to happen, because during that time, that the gravitational field changes very rapidly compared to its non-adiabatic, changes very rapidly on time scale that is comparable to the synodic period of the neighboring planetesimals. So they will destabilize their orbit. And some of them will get thrown out, some of them get thrown in. Now, if you come up with a planetesimal, which is small, like lunar size or Earth size, that's a small object, it will dissolve in the envelope. When it dissolves in the envelope, the heavy elements will settle down to build the core. But if you have 10 times the Earth's mass embryos, okay, there are plenty of them because these are oligarchs. There's plenty of oligarchs we know from, you know, Asian history, right? And when one oligarch becomes a king, what does he do? He kills all of the rest. Okay, the rest of the oligarchs, some of them are actually joined the embryo, and they will get all the way to the core. Okay, they have a collision all the way to the core. When they hit the core, now all of a sudden you have a huge amount of energy release, and that convection will dredge up all of the heavy elements. You destroy the core.
Another question? Yes.
So you mentioned the possibility of these super undergoing migration to very small radii and back out. So, you know, in the solar system, there's no evidence for migration of either planets or the asteroid, though. What needs to happen here?
Very good question. Okay. Now, so whether you can migrate like this or not. Okay. First of all, the solar system compared to the super Earth of all of the Kepler system, you look at them. It's very different. Not only the gas giant didn't go all the way in, but inside the orbit of Mercury, there's nothing. Okay? Now, you could say, well, you know, they just didn't condense. Well, that's nonsense, because we see plenty of them get condensed. Okay? And this process of forming this first generation and move out, and you can clear all of that in the inside. Okay? But then the question is, can you leave behind something to eventually form the terrestrial planets? I described there are 500 to 1,000 kilometer objects you can leave behind along the way. And then you get a gas giant form out there. So whether the gas giant return or not depends on the depletion time versus the migration time. And this is a remaining outstanding issue, but one can see that competition, if you can deplete the gas fast enough compared to the migration time, they will stall. They won't go in. In fact, only 10% of all gas giants, all known gas giants, actually end up as hot Jupiters. It's a small fraction. And those are the ones which manage to maintain the disk long enough so they can migrate.
When and how did the Earth get its iron core?
Very good question. And it's a very subtle but very critical question. Now, the Earth perhaps got its iron core at 30 to 50 million years from these measurement of hafnium tungsten type of measurement. Okay, so how does this scenario jive with that? Right, so now the Earth possibly is formed at the second stage. In the initial stages, when I did all of this formation, all of these are talking about these are super Earths. But they are, as during the migration of the super Earths, it also left behind some of the embryos, some of the planetesimals, which was scattered around into these regions. So when Jupiter formed, Jupiter had a small perturbation from Saturn. It had a small eccentricity. And it started to perturb all of these guys on the inside. Okay? But Jupiter's orbit also persists because there's a disk which has a gravitational potential that causes orbit to move around not like a fixed ellipse. When the disk goes away, the precession rate slows down. Okay? So the location where that precession rate matches with the precession rate of the planetesimals, their eccentricity gets excited. When your eccentricity gets excited, they cross each other's orbit. When they cross each other's orbit, that enhances the probability of collision. And this is when this resonance actually propagates inwards from the region of the asteroid belt all the way into the interior of the orbit of Venus. And the time scale for this transition is about on the time scale of tens of millions of years during the total depletion of the disk. So this process could also have left behind a selection effect. It actually cleared out a lot of the asteroid belt. It cleared out the small objects, it cleared out the large object, but the intermediate objects, which are not so subject to eccentricity damping, are left behind. And that's why we see in the solar system the size distribution in the asteroid belt what it is. And using this process, you form the asteroid belt first, and you form Mars second, you form Earth third. Actually, you form Jupiter first, and asteroid, and Mars, and Earth. If I have to make a prediction, a safe prediction, that Venus is probably formed more recent than that. But that requires sample return, which is almost impossible to get. So that prediction is safe.
Do we have another question for Doug? All right, if not, Doug, let me present you with this. And, thank you very much.
Thank you. Thank you.
Since you successfully answered all the questions.
Thank you. If they're wrong, should I return it back to you?
Absolutely. With interest.
Thank you.